Since we understood about the time complexity and the space complexity of an insertion sort algorithm, and the best case time complexity is order of n, and the worst case time complexity of an algorithm is order of n square, and the space complexity of an algorithm is order of 1. Now I just want to show you all of these things through the graphical representation so that you get a better idea about how the time getting changes with respect to my input value that is equal to n, right? So suppose I have the two axes. So this is my axis 1 or the x-axis, or this is my y-axis. So here the x-axis values represent the value of n, and the value of n range between 0 to 100. And the y-axis is my output here, right? So output in the form of a running time. As the value of n increases from 0 to 100, so you can observe how the functions behave here. So the brown line, so this is the brown line I have. The brown line represent how the running time increases if the time complexity is linear, right? Now let's write down more formally using some form of a function. Let's say I have a function f of n is equal to an plus b in the case of the best case time complexity, right? So this represents the best case time complexity. Now let's also define f dash of n. This is for my worst case time complexity of an algorithm. So a dash n square plus b dash n plus c dash, which represent the worst case time complexity, right? So here I just written them as a function so that we can plot and understand them clearly. Now as the value of n increases, right? So the value of n increases, how does the n change here? It increases the straight line here. You see the straight line I have? That's why the graph n looks like a straight line here. So how does the n square change as the value of n increases? N increases much faster here, right? Much more rapidly than n here. So the curve n square raises much more steeply compared to the straight line of an n. So in this graph, this curve represent n, and this curve represent n square, and we have n log n also, another curve which represent the n log n. You might wonder where n log n comes from. So don't worry about that. We will study an algorithm with the time complexity soon. So you are going to find a time complexity of some algorithm which is equal to n log n. For example, the next sorting algorithm which we are going to learn is call it as the merge sort. And the time complexity of this algorithm is order of n log n. We will discuss this part little later in detail. For now, just observe the two things. One which is n and another one is a n square. Right? So if n increases from 1 to 100, right? The value of n increases also from 1 to 100. What about n square? It ranges from 1 to 10,000, right? So that is what you can clearly notice from this example. Imagine if the values of n range from 1 to 1000, right? So in this case, this line is a straight line. You are going to get the same line same like here. It is linearly increases, right? The line n increases steadily, but the curve n square, if you look at this n square, increases drastically. If you increase the value of n from 1 to 1000, the growth of n square becomes too steep that you can barely see n or n log n in comparison, right? The n square term dominates the graph. So in a nutshell, what does order of n here? What order of n means? The input size increases. Let's say my value of n increases. The running time also increases proportional to the value of n here. So what does order of n square mean? Order of n square means that as my value of n increases, the running time increases proportional to n square. So even though the function may also contain the value of n and 1, the constant term, but this term dominates a lot. Right? The n square term dominates the growth for large value of n here. Now what about order of 1? What about order of 1 here? Order of 1 means it's a constant time or the constant space in this particular case, right? Because my space complexity is order of 1. That is the constant space. So it doesn't change no matter how large the input size becomes. this value doesn't change. So this is the intuitive way of understanding of a big O notation. In the next few videos, I will explain the formal mathematical definition and we will dive deeper into that.